expected number of students. Expected number of collisions. Sounds familiar? Expected number of collisions from homework, right? So every time somebody throws at you an expected number of, you should think about that number of, it's probably x1 plus x2 plus x, how many? Where each one of the x's corresponds to the items I'm doing expectations over. So if it's expected number of students, each x is a student. If it's expected number of chairs, each x is a chair. Expected number of collisions, if x is a collision. It's expected number of bins, balls, whatever. It's useful to think about it doesn't work all the time, but it's a classical way to solve problems. Expect the number of something, you break that into variables that are easy to compute the expectation of, in such a way that when you sum up these variables for your outcome, you get exactly the number of heads. Remember the coin? Expect the number of heads as an example. So expected number of heads in n tosses is the expected x1 plus x2 plus xn, where each variable xi is 1 if I see a head at toss I, 0 if I see a tail. That's what we did last time in class. And then expectation always distributes over these variables. That's easy. You got to make sure, though, that when you toss the coin in here, in this example, the number of variables that end up being 1 corresponds to the number of heads. That's what you want, right? So if you want to do expected number of collisions, you have a variable for collision. Make sure the number of collisions ends up being that sum. And then, of course, you have to compute the expected of each one of those. It's presumably a much easier problem than computing expected over the sum. So that's directly related to the problem you want to solve. In this case, I'll have n times e of xi, because all of them are the same. It's the expectation of heads in a toss, and I can compute the expectation of heads in one toss, which is an easy problem, right? It's half if it's a fair coin, or it could be, it's a bias of the coin if it's biased. So that's a very classical way of solving problems, and this is not an honor thing. We're assuming that after this course, you guys can handle this idea of breaking expectation into sums. So how about a problem related to this? Let's see, I have things a little bit out of order. Did we do one last time? I forgot. We said, what's the expected number of balls per bin? Did we do that? Is that what we did last time? Because I think I gave an example of this. How many balls per bin? What's the expectation in bin 5? How many balls you're going to get in there? So how would I do that? I don't want to write it again. Just recap from last Friday. Suppose I have a few bins, and I have a bunch of balls, and I throw the balls into bins, like the regular balls into bins process, and I'm asking what's the expected number of balls in bin 3? What should be my x1, x2, what are those variables? Again, my question is, what's this? Okay, let's write it down. Expected number of balls in bin 3, in a particular bin. How do I write this as a x1 plus x2 plus xn? Who is this x? What's the x corresponding to? Yes?
Each row.
Each ball. Right. So this is this ball 2 in bin 3, and 0 if ball 2 not in bin 3. I'm illustrating the concept here. If I want to know how many balls on average are in that bin, I look at every ball and say, is that ball in that bin or not? Is that ball in that bin or not? So in this case, the balls are distinguishable. What I have to verify before doing this is that this sum will correspond to the number of balls. Is that true? If I define these random variables, I throw the balls, I measure 1, 0 for each ball, but only for bin 3. So I'm not care about the other bins here. Is this sum corresponding to the number of balls I end up in bin 3? So then the expectation distributes. And now I have to compute expectation for each one of them. That's a much easier thing to do. Right, it's just simply the chance of that ball falls into that bin. So how about related to this problem, I want to do expected number of empty bins. So that's not the number of balls into one bin. You throw those balls, say you have n balls into k bins or something like that. How many bins on average are going to be empty? Like no balls falls in there. Can I apply the same thinking strategy? No? Or yes? I think I can. Here's my random variable. I'm going to find xij here. One, if ball I misses bin j. Misses mean goes to the other bins. Every ball has to go into some bin. So misses is the opposite of falls into bin j, right? And 0 if ball I falls into bin j. So this indicator is, I have a lot of these indicators. Here the indicators are not per ball, not per bin, but for every ball bin pair. So if I have n balls and k bins, how many of these xij's I'm going to have if I have 20 balls and 6 bins? If I define xij for every I and j. How many? How many of those random variables? That is not a hard question, right? Okay. So how do we compute this expectation here? This one. Expected number of empty bins. So who's xj? Product of all I. This is for bin j. Is product for all I of xij. So I want to say this is, actually let's not call it x, let's call it b from bin. It's expected of bin 1 plus bin 2 plus bin k. So each one of these bins, bi is 1 if bin j empty, 0 if not. So if b is measure emptiness, right? How many ones I have here correspond to how many bins are empty. That's what I want. But then I write down these variables bj. That's the same as before. I want to sum them up. Now I have to say I'm running this on particular this problem. I'm running this equation, which is bj. If you want bj, that's the product of these individual random variables for a fixed j. So b2 is the product for all I. Those are the balls of xi2. Why is that true? Is that true? So it's saying this is a 1 or 0 thing. It's either empty or not empty. These also are a 1 or 0 thing, but they mean something else. 1 if misses, that being 0 if not. So is it true that if you want this to be empty, probabilistically that means it's the product of all these guys to be 1? So empty 1, it only happens when all of them missing, right? All the balls have to miss this bin. That means all the balls, considering just bin 2, have to have a 1 here. If one of them falls in there, then the bin is not empty, so I get b equals 0. If all of them misses 1, 1, 1, 1, 1, then the bin is empty, 1. Remember, 1 means empty. Yes?
Sorry, no question. What is the big pi mean?
Big pi? What is big pi?
Sorry.
That's okay. I equal 1 to 10 of Ci. Means what? Yes, somebody.
I don't know the best way to explain it, but it's like summation, but with products instead.
Let's forget about summations. It's just a product. The sum is C1 plus C2 plus C3 plus C4.
Okay.
No, it's just a matter of notation. It's not nothing new. Like it's a product. When I say it's a pi, that means a product. When I say the sigma, that means a sum. But do we believe this thing? If you want this bin to be empty, you need all the balls to miss it. So you want this to be 1, that happens when the product is 1, aka all of them are 1. If one of them is 0, the whole product becomes 0. That means the bin is not empty. So now, can I say this expectation here is the expected over the sum of Bj, which is expected, it's a sum of expectation of Bj. We already know that because the sum always distributes the expectation. But now I'm going to say each expectation is the expected of this product, the pi, right? And I'm going to distribute the expectation over the product. Can I do that? Did we study something with expectation distributed over products before? When we distribute expectation over sums, we also look at how expectation distribute over products, although that was more complicated, right? How did that work? Over sums, it always distributes. Expectation of a sum is a sum of expectations. How about over products? That's it. Independent. So it does distribute if independent. So I'm going to do here exactly that. I'm going to say it's a sum of each expectation is a product. So it's a sum over j, product over I of xij. And now this is the sum over a product, here is sum over I, product over j of the expected of xij. Are those x's independent? Can I do the distribution over products? When I look at the bin and I say ball 1, fall there or not, ball 2, fall there or not, ball 3, fall there or not, are those independent? Are the throws of the balls depending of the other balls? Or there is, every ball has the same chance of falling there independent of where the other balls went? So that's why I can distribute the expectation. So now, what is expected of one of those things? So what is one expectation? Is a product over all the balls of this. Now, what's the chance, what's the expected of one of these xij's? Let's look at it. It's 1 if it misses, 0 if it's in. So what's the expected of that? What's the chance to miss or to be in? Because this is a binary random variable. For binary random variable, the expected is always the probability of xj equal 1, right? That's what it is. Because it's 1 times that probability plus 0 times the other probability. So it's that. What's the chance of missing the bin? I look at the ball, I look at a specific bin. This is bin j. What's the chance of not throwing it into bin j? It's 1 minus the chance to throw it into bin j, right? So this is 1 minus probability of ball I falls in bin j. So how much is that if the balls are thrown at random? For a ball, I look at the bins, and one bin that matters to me, the jth one, and then the other k minus 1 bins, right? The chance of picking that one is k, 1 over k, missing that one is 1 minus 1 over k. So then how much is this gonna be? This thing in here, for one bin, I think that's gonna be 1 minus 1 over k at power n, right? Because it's a product of these expectations. Each one of them is 1 minus 1 over k. But how many things are product? This product is for I equal 1 to what? The product is over the balls or the bins? The balls. So it's the same thing, 1 minus 1 minus 1 over k, n times product, so that's at power n. And now, this is in here, this sum is over all bins. So I've got sum over the bins, j equal 1 to k of this thing, 1 over k at n. This is the same for all terms. How many are here? K, so that's got to be k, 1 minus 1 at k. Because it's 1 minus 1 over k at n. But it's k times, because the sum is the sum over multiple expectations. So what did I do here? I kind of apply that idea with breaking the expectation into parts. I have an intermediary variable, which is the bin, empty or not. But then I have a more dedicated variable, ball into B or not. And then there's a relationship between them. If I want the bin to be empty, I need all the balls to miss that bin. So it's a product in here. Because if either one of them is 0, this will be 0. The bin is not empty. So then I follow the expectation calculation. I'm down to this particular probability of 1 minus 1 over k. That's the probability of missing a particular bin. Then sum of products, I get. Here's another one. Wait.
Can I ask you a quick question?
Go ahead.
So I'm gonna be honest. I understand the math you're doing. I don't understand at all why you're doing anything you're doing. But I'm just kind of curious. Do I need to know that formula and how you got there, or just the formula?
So unfortunately for you, the math is not the part that I care about that much, the arithmetics. Like if somebody does this right thinking, but he messes up somehow the 1 minus 1 over k, I say that's good. What I would really want you guys to remember is the plan, the master plan, not the exact calculations. The master plan was, I applied the same idea like in here. I broke my expectation into a bunch of variables. That's pretty much a lot of those problems with a number of things solved that way. So I want number of empty bins. I break it into variables. What is variable going to be related to? A bin being empty. So bin 1 is the first bin empty or not. Bin 2 is the second bin empty or not, so on and so forth.
What I'm saying is I just don't get it, so what do I do? So like, do I, like, what do I?
You have to follow the steps, maybe more like a step-by-step kind of thing.
Okay.
Okay? So I look at an expected number of stuff. The variables will be for that stuff, whatever the stuff is. So I'm looking for empty bins, right? I'm going to put a variable for every empty bin. That's B1, B2, B3. But now I have to relate those bin variables to what balls do. So I'm looking at this and I'm saying, a bin to be empty, I break that into all the balls must miss it. Those are the two main points that are the master plan. The rest is just calculations. Hands up who's with me. So he is not with me yet. But hands up who is with me. What's the master plan here so far? I break my empty bins into bin 1, bin 2, bin 3. Empty will be 1 here because I'm counting the empty bins. And then each BI, I'm saying that's a product over xij's over the ball. So j is the same j here. Maybe it would be easier if you don't follow this, which I think it's reasonably easy to follow. If can we compute directly the expectation of B2 without the x's? If I'm to say I throw n balls into k bins, what's the expectation that bin 3 is empty? Can I do that directly without those x variables? Like, I think you did that with counting, more or less. When you say, well, to be empty, all the balls must miss it. That's a product of things, because the balls are independent. What's the chance of one of them missing it? That is 1 minus 1 over k. And there's n balls, so it's that to the n. That make more sense? This is the same thing as written here, but I call this ball bin random variable xi. You could compute, I think, directly expected value of B2. That would you have to think, well, this B2 would be number 2. What's the chance of being missed by all balls? It's a product of all the chances of each ball miss. The important stuff in here is that this is an independent throws. So that's why the product works, which is the same reason as the product rule works. All right? That's the best I can do for now. Here's another one. Coupon collector. There's n types of coupons. Yes.
For this question, are you overcounting? Like if you have, for like example, for bin 2, if you're checking to see if that was empty, then bin 3 is empty as well. Are you overcounting?
I'm not measuring if one bin is empty, or if at least one bin is empty. I'm measuring the number of bins that are empty.
But like if bin 2 is empty and bin 3 is empty, when you calculate the expectation for 2 to be empty, you're including that one when it's 3 as well. And
So
then 3,
if both bin is 2 is empty and 3 is empty, I'm going to have 2 and 3 being 1, right? And the others being 0. Right?
Yeah.
The question you asked relates to the fact, how come the expectation of this sum becomes the sum of the expectations? Right? So you have to trust that one. Like, expectation of a sum would always be the sum of E of B1 plus E of B2 plus E of B3. Even though they're dependent. Because I think what she's asking effectively, wait a minute, if balls make bin 2 empty, isn't that more likely they kind of go in B3 now? Because B2 empty and B3 empty are not independent events, right? If a bunch of bins are empty, it's a much better chance that the other bins are not empty, because those balls have to go somewhere. So you have to trust the fact that even these are dependent variables. Do we realize this, that those are not independent variables, those b's? If I tell you that some of them are empty, do I change the property that some others are now not empty? Of course, because if the first 3 are empty, then it's like putting the balls in the other 17 bins. That makes it more likely those other 17 are not empty. But even though they are dependent, the expectation still distributes. Which means we have to compute just the expected of one of them. We don't have to worry about where the balls fall. Just what's here B1, here B2, here B3, so on and so forth. Perhaps that's, if with what you've done so far, it's easier to just do directly E of B1, right, without the X variable. What is the expected value of B1? B1 is either 1 or 0, so it's essentially the probability that B1 is empty. That should come out to 1 minus 1 over k at power n. And then this k here is because I have k bins. So I sum up k of the same. Anybody else? Yes.
So why don't you have to account for the fact that it's not totally independent to the bins?
They're not independent.
Yeah, but why don't we have to account for that when we're giving you the expected value of the bins being empty?
So you don't remember the x plus y is e of x plus e of y? Even if they're dependent?
I remember that.
Right. So that's what I'm saying. Even if b's are dependent, it's still e of b1 plus e of b2 plus e of b3. And they are dependent. The observation is very pertinent. If those balls go into bin 1, they don't go into bin 2, so it does change the probability of being empty. Those are not independent variables. If I tell you half of them are empty, it definitely changes how the other half behaves. But you have to trust that this works. Remember, for dice calculation and for other things, it always works out. But assuming we trust this formula, is everybody comfortable with computing expected of B1? Just one of them. What is the chance that bin 1 is empty? That's the chance of all balls missing it. Now that's independent. The fact that I have n balls and I look at B1, it's either in B1 or outside in some other bin. The throws of the balls into bin 1, those are independent of each other. So I look at this product here and say, if any ball falls in, that's done, it's not empty. I need all the balls independently to fall outside bin 1 for B1 to be empty, Bj in this case. Anybody else? All right, let's do another one. Coupons. So the question is, how many coupons I need so the probability is uniform. Probability of any type, type 1, probability of type 2, probability of type n is 1 over n. How many coupons at random in expectation until I collect all types? So the coupon collector problem in basic terms is somebody is trying to collect all types of a coupon. There's n types, and I'm trying to, like achievements in the game, right? There's like 17 achievements, and I'm trying to get all 17. And every time I get one, it's a random one out of the 17. How many times I have to get an achievement or a coupon? How many of them total until I get all of them? So my plan is to play the game enough to get achievements until I cover all 17 achievements. And that says, well, how many coupons or achievements you have to collect overall? Here's the issue. The first time when I get the coupon, is that a new coupon that I haven't seen? Definitely. The second time when I get the coupon, I'm not guaranteed to be a new one, right? If this will be what we call without replacement, suppose I have a bag of n coupons, one for each type. How many times I have to put my hand into the bag and get the coupon until I get all of them? Trivial question. N times, right? Because it's without replacement. That is, every time you put your hand into the bag, you get a new coupon. However, this is not like that. Every time, this is with replacement, right? So every time you put your hand into the bag, you get the coupon. The first time is a new coupon. But then the second time, you have a probability to get the same coupon. So that's not good, right? You do it until you get a second coupon. Now it's even harder because now I've got 2 coupons. It's a larger probability to get one of the ones I already got. The more coupons, new different coupons I get, by the time I've got n minus 1 coupons, so I need just one of that type I haven't got yet. That's much harder to get, right? Because every time I get a new coupon, there's n minus 1 over n chance that I'm getting one that I already have. So this is the kind of achievements, you know, like the more you get, the harder it is to get new ones. So this place, until I collect all types, that's deterministic. So I'm not asking, just for avoiding confusion, how many types I collect on average. I'm not, the other version of this problem is, if I get 100 coupons, how many different types I'm expecting in 100 coupons? I'm not asking that question. That's a start problem for you to take home. I'm asking, if I really am perseverant to collect all coupons, how many coupons on average do I need to collect to kind of get all? Expected of how many coupons. How can I break this into that? If I break it into x1 plus x2 plus xn, what should each variable correspond to? Who should be x1? Not coupons 1, but how many coupons I need until I see the first one. So number of coupons until a first new one. How many? That's 1. The first coupon is not a random variable really. The first coupon is going to be new. Who is this? The number of coupons until second new. Right, so this is a little tricky. Who's x3? Number of coupons until, so I mean after the first one, right? After I see the first one, this is how many coupons I need to get a second new one. And after I see 2, so given I have 2 types now, how many coupons until the third one? Right? And the last one, xn, what's this gonna be? Given n minus 1 types collected, this is the number of coupons until last type occurs. So how do I do this? Back to the expectation formula. What do we know about the expectation for some? Even if they are dependent, doesn't matter what they are. It always breaks into expected of x1 plus expected of x2 plus expected of xn. So who's expected of x1? That's easy, that's 1. Who's expected of x2? How many coupons do I need until, yes. How many, so I have 1. I've seen 1, type 1. And I pick coupons now until I see a second one. Obviously that's like, let's see, so that sounds familiar at all? Yes.
Is it one that's already accounted for?
The expected of x2, you say it's n minus 1 over n? I think you mean the probability of getting a new
The
coupon.
probability of getting the expected.
So we want to see what is this, and what she's saying, the probability of new coupon is like in 1 trial. That's what you're saying. in one trial. It's n minus 1 by n. Why is that? I have already one. If I put my hand to the back to get one coupon, there is 1 over n chance I'm getting the same one like I've got, and n minus 1 chance over n, right, to get a new one. But that's not what this expected of x2 is. And that's a good observation. Expected of x2 is how many times I need to repeat this process on average to get a new coupon.
Is it n over n minus 1?
I don't know. So you're saying this in here, it's n over n minus 1? Why is that?
Because it's just one over the probability of you getting it this or
So he's saying this is 1 over the probability of we just computed. Is he right? Is that a guess? Or me? I just wrote what he said. He's saying, I think I was guessing. He's saying if the probability to succeed, that's what I want to do here, get a new coupon, right, is this guy, then the number of times you need to try that on average to succeed, it's 1 over that probability. So as a general rule, if the number of success, I'm trying to date a girl, right? And my chance of succeeding, you know, I call her and she says no to me, that's a failure. My chance, say it's 75%. It's not that high, but let's say, right? He's saying, well, the number of times you need to try to date a girl to succeed is 1 over 75%. And if that would be only 25%, right? So every time I call a girl, the chance of saying yes, it's 1 out of 4. He's saying that the number of times you need to try to get to date the girl is 1 over that, that's 4 times. Is that the general rule? But, you know, if it is, we need a proof, right? So let's take that rule. If the probability of success is P, the number of trials expected until first success. Because the first success is what, this is clearly the first success, right? By success I mean get a second type of coupon. Is 1 over 2. Everybody knows how to prove this theorem? If that's true, that's his conjecture right there. We don't know. Everybody gets why this is n over n minus 1? We established the probability of success, it's n minus 1 over n. Then the number of trials until I succeed would be 1 over that n over n minus 1. If that's true, what's the story with E of x3 here? What is the chance of success for E of x3? The success, once I have 2 coupons collected and I try another coupon, what's the chance of success? N minus 2 over n. And the expected, assuming this conjecture is correct, will be what? N over n minus 2. How about the last one? E of xn. What is the probability of success? When I'm at the last coupon, I have n minus 1 of them, I just need the last one. Every time I put my hand into the bag, I get 1 coupon. What's the chance of getting the one I don't have?
1 over n.
1 over n. So the expected number of trials until I get that one will be n. 1 over n, that's it. That's all very good, assuming this, right? Which nobody knows how to prove, apparently. It's in the notes somewhere here. We have to find it and dig it up. Okay, well, let's prove that then. Here's our theorem here. We can formulate that easily in terms of coins, right? How would we formulate the same theory with coins? If I have a coin that has bias P for probability of head, what is this question? Number of trials expected until first success. Expected number of tosses until what? First head. Is that the same exact question? It is, because this is a P1 minus P. It's a coin thing. It has only two options, success or failure. And every toss or every hand in the bag experiment is independent. Well, so if we do it, let's figure out what this is. So remember the problems from the recitation. I think is like if the number of tosses here, this can be 1 or 2 or 3, so on and so forth. And the actual sequence, this is head, this is tail head, this is tail head. Remember we've done this at recitation. We had the problem where in order to stop up the first head in a one toss, you gotta get that head. After two tosses, you must have tail head, tail head, so on and so forth, tail head. And the probability of this to happen, what's the chance of a head in the first trial? P, right? What's the chance of tail head? 1 minus P times P. Because tail is 1 minus P. What's the chance of tail head? 1 minus P squared times P. What's the chance of, this is K minus 1. 1 minus P at K minus 1 times P. So now the expected, that expectation is the probability multiplied with the value, right? It's sum over n equal 1 to infinity of n times 1 minus P at n minus 1 times P. Is that right? So for 1, I got just the P, because 1 minus P at 0 is 1. For 2, I get 1 minus P times P, and it sums up. Of course, this P is in the front, right? It's P sum from n equal 1 to infinity of n times 1 minus P at n minus 1. So what do we want to get here? That this is 1 over P. So how do we do this? Let's write it down in that I'm breaking the sum into explicit terms. So let's call this value we want E. Anybody has any clue how to do this? There are many ways to do it, but we will do it the high school way right now, so that first, and then we'll see if there's another way. Here's a trick. If I multiply with 1 minus P in both sides, what do I get? P times 1 times 1 minus P, right? Plus, I wonder if we need P in the front. Let's keep the P in the front. P, this is 1 minus P now. This is 2, 1 minus P squared, because I'm multiplying with 1 minus P. 3 times 1 minus P cubed, right? Plus 4 times 1 minus P fourth, plus da da da. So now, I want to do a subtract one from the other. So, which one is the easiest way? I think subtract first minus second. So I'm doing the first minus the second. E minus 1 minus P, right? That's on this side, because I'm subtracting from the top the second one. P is a common factor here. It's a common factor here, so I can leave it as a common factor, right? Now, 1 minus this, I get a what? Let's see how, I think I want to put this one separately. This one here goes first. And then I want to subtract it this way from now on. How much is 2 oranges minus 1 orange? Orange here is 1 minus P. I have 2 oranges, I take 1 out, I get what? I get 1 minus P. Plus, now the orange is 1 minus P squared. I have 3 oranges here, minus 2 oranges here. Because it's the same orange, right? 1 minus P squared, 1 minus P squared. I have 3 here, minus 2 here. What do I get? 1 minus P squared. Now, from here, 4 of this orange, 1 minus P cubed minus 3 minus P cubed. How much is that? 1 minus P cubed. Plus, I'm going to get 1 minus P 4, plus da 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 da. So, if I simplify the e's here, I get PE, right? Because E minus E goes away. I get PE. It's P times the sum here for, say, k equals 0 to infinity of 1 minus P at k. Because at 0, I get 1. At 1, I get this guy. At 2, I get this guy. At 3, 4, 5. That's the sum of all the terms in here. Right? So P goes away with P, and I'm left with E equal this. Anybody knows how to sum this up? The geometric series? The one that looks like 1 plus R squared plus R cubed plus R to the 4 plus 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 plus. Anybody knows the answer to that? Yes.
The first term upon 1 minus R.
1 over 1 minus R, like that?
Yeah.
So how much is this then? 1 over 1 minus the base, 1 minus P. So that is 1 over P. I know it sounds fancy, but it's not. Geometric series, everybody will be dreaming geometric series in about 10 days. Not just you, the whole regular class. So we'll get there very soon, and then you'll see why that's true. But it's something you can easily prove yourself. What is fancy in this proof is the creative idea how to get rid of these 2, 3, 4 guys. These are pain. If it be just 1 minus P, 1 minus P squared, 1 minus P cubed, that's okay. But these 2, 3, and 4 are a problem. So this whole mechanism would multiply with 1 minus P and subtract. The whole design is to get rid of these coefficients. See what happens when I subtract from 2 oranges 1 orange? I'm left to just 1. From 3 to 2, just 1. From 4 to 3, just 1. That's a mathematical trick of telescoping to get rid of these annoying coefficients here. So that's 1 over P. We proved this. We're good, right? We also proved this problem, which is if you want to date a girl or you want to flip a coin, and the chance of success is P, how many trials you need to make to get that first success. And then we can apply this result in here. The first success comes right away. Here it's 1 from the first coupon. In here, the probability of getting a new coupon is n minus 1 over n. Therefore, the expected number of trials is n over n minus 1. all the way to the last one, which is 1 over n, probably d. Therefore, what's the expected value? Be n, right? So we can sum up those things. It's 1 plus n divided by n minus 1, right? Plus n divided by n minus 2, plus n divided by 1 over n. That's the last one. So this will be something like n times 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 3 plus 1 over n. This is backwards. N times 1 is this in here, and n times 1 over n is this one in here. So I write it backwards. This has a name. It's called Hn in mathematics. This particular summation. 1 over 2, 1 over 3, 1 over 4, so on and so forth. And if you want to impress me, you can prove that this is very much natural logarithm, very close to the natural logarithm of n. Not exact, but within 1 unit of the logarithm of n. So then the answer to this question is n times log n, roughly. How many coupons I need to collect to get all n types, n times log n. So in this problem, there's a lot of ingredients. There is the basic break the expectation into variables for each coupon. Then there is this success probability. The success is P. The number of trials until I get to success is 1 over P. And then there is, how do you compute the whole thing? You have to know that this harmonic series, that's how it's called, it's roughly logarithm of n. Now we will do this later, and the geometric series later. But this part in here, the probabilistic part, should be accessible right now. Right, let me see if I have any more problems. Somebody was asking me, where's the entropy? Yeah, let's do it right now, so you can leave. It's already late for you?
It's fine.
All right. So there is this entropy problem that I haven't done, right? And you guys need it for the homework and for the recitation. Let's do that. So I have a distribution. 1, 2, 3, up to n, and the probability P1, P2, P3, up to Pn. Of course, they have to sum to 1. The entropy for distribution, remember, expectation and variance depend on the actual values. Entropy does not. So this is a distribution over students, objects, numbers, whatever. It doesn't matter what are those values, because in the entropy, they won't matter. This is the sum over all i's, pi, log of 1 over pi. That's what we've done when we talked about the entropy the first time. This is maximum if P1, P2, P3, Pn is uniform. And that maximum we can calculate. It's the maximum is log of n, right? Because 1 over n is n, log of n, and it's sum over 1n, 1n times is log of n. And the minimum is when a bunch of them are 0 and one of them is 100%, 1. Then the maximum, the minimum is 0. So this is a measure of randomness. If this is uniform, is the most random. And this is not random at all. If every time I roll a die, I get a 6, that's not a die anymore. I know for sure I'm going to get a 6 all the time I roll it. that has no entropy. So the smaller the entropy, the smaller the randomness. The more entropy, the more uniform, the less I can predict what's going to happen. With a die that's uniform, you try to make any prediction about the die, you're going to be only right 1/6 of the time, and you're going to be wrong, 84% of the time. But the more Q the die is, say the die only produces 5 and 6s, by predicting a 5 or 6, you will be rough half of the time. The more you can predict things, the less random they must be, the less entropy they must have. So here's why this is important. Let's say I have a B, C, D, E, F, G, H. These are symbols that via an encoder, they must be bits. So when I'm sending those symbols over a communication channel, like via my cell phone, I have to encode each symbol. They could be letters, characters, names, whatever. I have to encode each one of them into ones and zeros. So for example, such encoding might be A00, B01, 100, 101, 1100, 1101, 1110, and 1111. As an example, right? So I have a table here. It says the only thing I'm going to send to my channel communications are some sequence of A, B, C, D. So if I want to send the sequence B, A, F, what am I going to send? If I send B, A, F, how is that going to look?
0, 1.
0, 1,
0, 0.
and then 1, 1, 0, 1, right? B, A, and then F. Well, so there are 2 questions here. 3 questions. How to come up with the codes? Like, how do you figure out A00 and B01? Right? Another question is, assuming each symbol has probability, so let's put some probabilities here. They're not uniform. 1/4, 1/4, 1/8, 1/8, 1/16, 1/16, 1/16, 1/16. So given probability of each symbol, what is the BPC? Is the average bit per symbol or character. So that is to say, if I have a string of many, many characters, could be A, could be B, could be C, could be D, and F, so on and so forth. They are not equally likely. 1/4 of the time in my string I'm going to see A's, 1/4 I'm going to see B's, and only 1/16 of the string is F's. So those letters in the string that I'm sending over my channel are not equally likely, or there's not 1/8, 1/8, 1/8, 1/8, 1/8. A's are more often than G's and F's. So average bit per symbol has to be with, if you send n symbols, how many bits you send total. So this is number of bits for n symbols divided by n. On average, that's what I mean. If I have a large piece of text that has characters in it with these probabilities, and I'm sending for every A 2, for every B 2, for every C 3. So in this example, that is going to be what? This is effectively the expected value, right? Expected of bits per symbol. How do I compute this? I mean, it's just the expectation formula, right? For every A I've seen, is the how many symbols I have for A times the probability of A, plus how many symbols I have for B times the probability of B, plus how many symbols I have for F times probability of sending F. So what is this calculation? How many bits do I have to send when I send A? For every A? 2 times probability of A, plus for B, 2 times the probability of sending B, that's 1/4, plus 1/8, 3, right? 3 times 1/8, plus 3 times 1/8, plus 4 times 1/16, 4 times 1/16, 4 times 1/16, 4 times 1/16. Ends up with this here. What am I doing? I have the symbols and text made of those symbols. I have to encode them in 0 1s to send them over a channel. They're not uniform. A's and B's are more often than C and D's, which are more often than these other guys. I'm sending, it makes sense, right, to send fewer bits for frequent letters, right? Because my purpose is to not send that many bits overall. I'm sending 4 bits only for infrequent letters and 2 bits for frequent letters. That should be much better than sending, say, if I want to send the same number of bits for everybody, how many bits do I need? 3 or 4? Can I encode all these 8 symbols with 3 bits each? Can I? Can I make it A000, 001, 010, 011, 100, 101, 110, 111? Which one do you think would send less bits, this guy or this guy? This is two different encoding schemas. You can encode A as 000, B as 001, 00, so on and so forth. And then how many, what's going to be my bit average per character if everybody has 3 bits? Average is going to be 3, right? Is that clear? In this case, average, this is going to be 3, because everybody sends 3 bits. If you have n characters, you send 3 times n bits. Divide by n, you get the 3. In here, how much do we get? Anybody did this calculation?
3.
How much?
3.
This is 3?
2.5.
You guys are less help than 2.75? Is that true? Anybody check this? So what's the moral of the story here? If you encode like a dummy encoding, everybody gets 3 bits. You're losing the fact that some of them are more frequent than others. You send 3 bits for everybody. If, however, you take into account the frequencies, you say, wait a minute, I can send 2 bits for every A, because A is very frequent. And I'll send, as a consequence of that, send 4 bits for the ones that are not so frequent. Overall, on average, I'm sending less. So the moral of this average is that if I do this here, I get 2.5, 2.75. So people saw this thing about 50, 60 years ago, and they like, okay, so how much can you do? What's the minimum per bit that you can send? Obviously, it has to do with the probabilities. What if I tell you 100% is an H? You have 8 symbols, but you're always going to send an H, okay? That's it. So how do you send n symbols? You only have to send n. Because since it's only H, you can tell the other guy, hey buddy, if I give you n, it's n symbols. You don't need to encode the symbol at all because it's always an H, right? In here, G, H, F, and E are less likely, and A, B are very likely, and so on and so forth. So, how does this work? There is a third point in here. Let's say this is 2.75 here. There's first a third point, which is decoding must be possible. That is, if I send this code on the other side, how is my friend on the other side going to decode this? He's going to see 0, 1, and he's going to see 0, 1, that's a B, right? There's going to be 0, 0, that's an A, right? And it's going to be 1, 1, 0, 1, that is a F. That sounds very good if that person knows where to break it. So you can imagine some codes that are not easy to break. What if I tell you A is 0, 0 and C is 0, 0, 1? You would have the problem when you see 0, 0, 1, you'll be like, oops, I'm not sure. I can break it after 2 zeros and get an A, or I can continue with one more bit, 0, 0, 1, and get a C. Decoding has to have the property that a code cannot be a prefix of another code. For example, 0, 0, 0, 0, 1, and 0, 0, 1, 0. Because if there are such prefix properties, when you see the string 0, 0, 1, 0, you're not sure, is it a 0, 0 plus some other bits, or it is 0, 0, 1 and some other bits, or is it a 0, 0, 1, 0 and some other bits, right? Is my code in here has that property? Is any prefix, would my decoder get confused in here at all? Is any one of those prefixes of another code? If I see, for example, 1, 0, am I confused whether that's a code or I should keep going, read more bits? See what I'm asking? Somebody gets a string, see 1, 0 in the string. Is 1, 0 a code? No. Reads another 0, 1, 0, 0. That's a C. It could be a C. It could be part of some other code, 1, 0, 0. Is there any other code that starts with 1, 0, 0 here? No. That's why it's a good code. Because once I read the sequence, I know if that's a code, if not a code, keep reading bits. If it's a code, that's the one. You can break it right there and say that's a C. Because no other code starts with 1, 0, 0. If I see 0, 1, can I declare that's a B, guaranteed? Is there any other code that starts with 0, 1? Because if there would be, I'll be in trouble. That's either a B or some other longer code, but it's not. So those are the three properties that we need. We want to come up with these codes in such a way that they're not prefix of each other, so they can be decoded on the other side. And the BPC, we want it to be small, large, what? Small, right? Who wants to send a lot of bits over the channel? The whole theory of encryption and communication has to do with encrypting the whole, let's say, cell phone service or whatever it is. I don't want to send that many bits, right, over the network. The more bits I send, without losing information, this has to be perfectly decodable. This is not the MP3 or JPEG that asks how much information can I lose before the guys can still see what's in the image. I'm not losing any information here. Everything is perfectly decodable to what it was. So how do we do this? Here's an idea. I build a code tree. think that's the code that I need for this. The code tree, it's a function of probabilities. So I'm looking at those probabilities. And I'm saying, this is the root of the tree, that's like 1. And I'm saying, this is 1/2 and 1/2. How much is this one here? 1/4, 1/4, 1/4, 1/4. This is 1/8, 1/8, 1/8, 1/8. I can keep splitting this as much as I want. 1/16, 1/16, 1/16, 1/16. If I want to keep splitting this 1/16, I'm going to be like, how much is this? 1/32, 1/32, right? I can keep down as much as I want. I'm trying to fit my characters into this tree. So A is 1/4. That means A should stop as a 1/4. So like this one here, that could be the A. This could be the B, because it's 1/4. Do I have another 1/4 in my probability table? No. Do I have a 1/8? So that could be the C and the D. How about another 1/8? No. So this is the 1/16 here. That should be the E, F, G, and H. So I draw the tree first, and then I try to see where those letters fit in. They fit very nicely. They're powers of 1/2. But if they're not, I have to be creative how to fit them into this. They're gonna sum to 1 because this tree always sums to 1. Every time I expand the 1/16, I expand into two things that sum to 1/16. So at any point in time, those things will sum to 1. So now that I've got this tree, can I assign somehow codes to it? So I have the tree. How would I assign codes? So what I did, I draw the tree, I fit in A, B, C, D, F, G into the tree. And now, here's what I'm saying. Everybody go left, that's a 0. Everybody goes right, that's a 1. 0, 0, 0, 1, 1, 0, 0, 1, 1, 1, 0, 0, 0, 1, 1, 0. Is that exactly how the code works? Yes. This is called Hofmann codes. Hofmann tree and the Hofmann codes. Let's do a quick, just to make sure everybody understood this. What if my probabilities will be very different? So A, B, C, D, E, F, G, and H. What if I have 1/2, 1/4, 1/8, 1/16, 1/64, 1/64, 1/64, 1/64. Hopefully that's a distribution. Right? 1/16 plus 1/16, that's 1/8, so it's a distribution. What would the tree look like in here? I start with a 1, right? I split it into 1/2. So who's this? A, because A is 1/2. And who's this? That's all the other guys together, B, C, D, F, G, right? So that's 1/2. And then in here, I split again. How much is each one of them? 1/4, 1/4. Do I have something with 1/4? B, 1/4. It's 1/8 and 1/8, right? So how much is this guy? That's a C, right? And in here I'll have nothing. I'll split this into 4 of, is that right? No, I have a 1/16. 1/16, that's the D. And then 1/16 in here. Now I split this into 4. So it's 1 over 64 each. Except I can't split into 4 because then I can't assign bits, right? 0, 0. I only have 2 branches with 0, 1. So I have to do multiple splits. This is 1, 32, 132. Now this is 164, 164, 164, 164. So who are those? E, F, G, and H. So what will be the codes here? 0, 1, 0, 1, 0, 1, 0, 1, 1, 1, 0, 0, 1, 0. So who's the code for A? Just 0. Who's for B? 1, 0. Who's C? 1, 1, 0. Who's D? 1, 1, 1, 0. Who's E? 1, 1, 1. How many ones are there? 1, 1, 1, 1. 1, 1, 1, 1. 0, 0. Who's this?
1, 1, 2.
G, 1, 0, and 1, 1, 1, 1, 1. Now, here's the magic. Because I have this tree, I can promise this property. There's no prefix codes. Because if there will be a prefix code, what would happen? In the tree, every code is the path from the root to the leaf. That's the code. If some other code will be the prefix, will be on that path somewhere, but not a leaf. But everybody's a leaf in here. All the A, B, C, D, F, G, H are leaves. For, say, C to be a prefix of E, that means the code to E is the path, and then C will have to be somewhere on the path to be a prefix, but not at the end, which cannot happen since everybody's a leaf. So this guarantees that prefix, a prefix free. Yes?
Why does the code tree have to be linked to probabilities? Because if you use the codes from the first example, wouldn't that be more efficient?
Why what?
Why does the code tree have to be linked to the probabilities? Like, why can't we just use like the one from the first example and the second?
So this tree corresponds to the first example, 1/4, 1/4, 1/8, so on and so forth, right? And
Why does it have to?
the tree has to correspond to probabilities because the lower the probability, the deeper in the tree you must be to have more bits in the code, right? So this G here, because 1 over 64, will have 6 bits. That means deep in the tree. And A will have only 1 bit because it's, up in the tree. C here, it's in the middle, it has 3 bits because its probability is somewhere in the middle. So the tree reflects by level.
I think he's asking, like, why is this way more efficient?
Oh, I'm getting to that. Just the tree, that's important to see about the trees. Very frequent items are very high at the top of the tree. Therefore, they have small code lengths, 1 or 2 bits. Very low frequent items are at the bottom of the tree. That's why they have 6. So the property that's magic of this tree here, that answers, I think, this question, is that the number of bits for a character is log of 1 over the probability of that character. Is that true? How many bits I got for A? 1 bit. What's the probability of A? 1/2. So log of 2 is 1. Log base 2. Is that true for every symbol? Is B the size, how many bits I have for B is the log base 2 of 1 over the probability of B? How many bits B has? 2. What's the log of 1 over the probability? Log of 4, that is 2. How about for, say, D? How many bits I got for D? 4 bits. That's log base 2 of 1 over the probability of D. right? Because 1 over the property of D is 16, log base 2 of 16 is 4. Would it work for these guys too? 1 over 64, log of 1 over that, that's log of 64, log of 64 is 6. That's why they have 6 bits. That's what makes this optimal. This property here, it's optimality. If every single symbol has associated a number of bits that is exactly the log over 1 of its probability, what will be the BPC for Huffman trees? It's the same like before. It's the sum over all symbols of the size of the symbols times the probability of the symbol, right? Well, we said who's the size of the symbol then, assuming Huffman trees? We say this is 1 over the log of the probability log of 1 over the probability of S, right? Times P of S. The size of S, how many bits a symbol gets, it's exactly log of 1 over its probability. And we saw that's true. We can do it here too. In this example, 1/8 is D. How many bits D's got? 3, because that's log of 8. How about these guys? They got 4, because that's log of 16. So what is this? This is the entropy of the distribution. There's a theorem in coding that says no code can achieve a BPC smaller than the entropy. That's impossible. Any code that gets less BPC, bits per character on average, than the entropy must lose information. It's like JPEG. You see the image, but you don't see everything. If you don't want to lose information, I hope that answered the question. The optimal way, the minimum BCC you can have is the entropy rate of the distribution. And it so happens that Huffman codes achieve that minimum. You can see right here. They associate the size of the bit exactly 1 over log over 1 of the probability. So when you compute the BCC, you get exactly entropy, which is a theoretical lower bound. Therefore, they're optimal. There's a slight wrinkle with what happens if these probabilities are not 1 over powers of 2. Because then how do you build the tree? It can still work on average. But the easy way to see this is exactly when probabilities are 1 over powers of 2. So, in terms of these 3 properties here, probabilities will dictate how much can you compress. That is, how small BPC can be. Because you want it very small, you need to have a low entropy to achieve a small BPC. The Huffman tree will answer this. How do you come up with good codes? You build a tree and you assign the codes left 0, right 1. And the decoding to be possible, I need to avoid prefix tree, which the prefix free, I have to have prefix free codes. That means a code cannot be a prefix of another code. And that happens with a tree if every single symbol is a leaf. So in here, I don't need this part of the tree, right? Because I'm done with here. At 32, I have done. So that's the entropy example that when you go over the homework and the recitation paper, we'll just look at this. It's in the notes, probably written a little better than I wrote it here. You have to have in mind those 3 possibilities. Now, the homework of the recitation paper might say use a different code, not the Huffman code, like this code. Is this code prefix free? Does it satisfy this property that no code is a prefix of another code? Yes, because everybody has 3 bits. No 3 bits can be a prefix of another 3 bits unless they are the same 3 bits. So this property is only interesting when you have variable length codes. When somebody has 2 bits and somebody has 4 bits, then you can ask the question. You may have a prefix code in there. That's a problem for decoding. All right. I still have to show you some things. I will lower down a little bit the theory because we can't push this into Tuesday, so we gotta finish it now. I'm gonna show you the sampling simulator, but I'm only gonna say something brief about theory. But I'm happy to discuss this with the people interested in the math. We talked about large numbers. And we attempted a sort of a proof based on an inequality. I think we should be inequality. So I'm not going to do any proofs, but I'm going to tell you what those two laws mean, law of large number and the central limit theorem. Those are very important results to know for any scientist of any field. The proofs, only mathematicians have to know them. But you have to know what those laws are. So if x1, x2, x3, xk, and keep going, xn, are IID, independent and identical distributed. Say the mean, we call it mean, it's expected, and the variance of all have the same mean and variance. We are particularly interested of what happens to the average. So I take a sample of some of them. So I compute my new variable y, which is x1 plus x2 plus xk divided by k. We wonder what's going on with the average. If I pick say I'm sampling from patients that have a certain diabetes score, or I'm sampling your midterm scores, or whatever. Sampling means I'm sampling few samples from the same exact distribution. What about the mean? The mean is a random variable. That's not the mean of all of them, it's the mean of the sample. So the law of large numbers says roughly this has to converge to the same mean. That's pretty intuitive. If you sample enough things, the expected value of mu have to go to that, if k is large enough. The central limit theorem says that y distribution is normal. It's actually not y, it's like square root k times y, but that's so normal means you have to get used to how histograms work. These are values and these are frequencies or counts. You're going to see a lot of those. Values, whatever you sample, either ages or scores or what. And somewhere here is the mu, the mean. And this is, if it's high, means it's likely. If it's low, means it's not likely. Here's the normal distribution, which I think I showed you already. The highest values are around the mean. And this is its variance, how wide this Gaussian is. A small variance means everything is very likely around the mean. It's nothing on the sides. A large variance means there's a lot of points far away from them. So this theorem, law of large number, says the expected value, the mean of the average, is the same mean as the variables you sample. The central limit theorem says if you sample those means for a particular k, the distribution of where the mean is, because if I sample 5 students, I get a mean here. If I sample another 5 students, I get a mean here. If I sample another 5 students, I take their average. The distribution of the means from the sample would follow Gaussian distribution, even though the x's are not Gaussian distributed. That is when you average, say, student scores that are not Gaussian distributed, or car prices, not Gaussian distributed, or house prices, not Gaussian distributed, or coins, ones and zero, clearly not Gaussian distributed, right? Because zero, it's a lot, one is a lot, middle is nothing. When you average those things, the average is Gaussian distributed if you average enough of them. And now because in nature, a lot of things are averages or sums, you know, then in nature a lot of things look Gaussian because they come from an average or a sum. And the central limit theorem says averages and sums are Gaussian distributed if you average enough things. So let me show you quick demo with a code that you can play with yourself. It's written in MATLAB, but you don't have to write anything, you just have to execute the code. So maybe you can help me with the light in there to turn off the lights from the board lights. Is the bottom closer to the, no, to the right. Yeah, that one. Okay. So here's the code. It's already online. And here's, I run MATLAB without the whole desktop, just command line.
So those are actual grades.
What?
Oh my god.
No, that's from a few years ago. Okay, so how this works? I look at my code and I want to sample one So this code, you type the name of the experiment, that's one of the names in the file. You say you want to do replacement without replacement. That is when you sample, you put what you sample back or not. With replacement, you always put it back. And this is at any episode how many items you take. That's 10. Every time I press a button, there's been 10 samples, right? So what's gonna happen here? I get a plot. This is what I've sampled. I sampled 10 things. I roll the die. This is the die roll. I roll the die. This is a histogram. This is the sample, the values I've got 2s, I've got 3s, I got 4 and 5 and 6s, and this is how many of them I've got, right? The frequency. I've got 3 2s, 1 3, 4, 2 4s, 1 5, and 3 6s. And if I press the button again, I'm sampling 10 more. So now if you see sample size right there, it says 20, right? Because I rolled the die 20 times. And if I sample again, I got 30, and 40, 50, 60. You know, every time I press the button, I'm rolling the die 10 times, right? So how many die rolls I have so far? 500. What should we observe about these counts? If I throw the roll enough, this is a uniform die. Should be roughly kind of uniform counts, right? Because it's a uniform die. Here is the sample mean. That is, I take all my rolls and divide by 5, sum them up, divide by 500. That's the red line. And I also print in there standard deviation. Standard deviation is the square root of variance. And the entropy. So what happens if I roll a different experiment? I want to roll, for example, one die non-uniform 5 to 6. Let's try this one. But let's run it, every time I press the button, 50. So that's another one. What happens to the average if this is a 1 and 6 biased? Remember from last lecture? I had that die that was biased on 1 and 6. So what's going to happen, I already run it 2,700 times. My MATLAB simulator is much faster than rolling an actual die. It's also much more exact in terms of probabilities. You'll be surprised how human hands, even well-intended, how cannot achieve uniformity. What do we notice? I've got a lot of 1 and 6s, but the average is the same. Let me show you two more. What happens if I sample those meters grades? 2017, right? Let's try that. That's not this one? There they are. Let's do meter my Here are the meters. And there's blue bars and green bars. Green bars is only the last batch, the last 50. The blue bars are the totals. So what was the average in 2017? Right there, the red. Something? Not that many people with 100 though. So suppose I sample a lot of these, right? Of course, with replacement means a lot more than how many people are. Then there were not 7,000 students in there, right? So some of them got sampled multiple times here. And what happens when I terminate this? I get a new plot. This is the plot of the average distribution. Every time I sample 50, I got an average. I sample 50 again, I get another average. This is the distribution of those averages. This distribution, if my 50 would be bigger, will look Gaussian, even though the midterms were not Gaussian distributed. This is the central limit theorem that says the sample averages, every time I press the button, I get an average. Those numbers were Gaussian distributed, even though my original sampling distribution was not. So please download this code. You can play MATLAB with it without learning any MATLAB. Just press the button and figure out which one you want. Yeah.
我可以从后面走。I know, I don't want to do it to him because I'm pretty tired. Yeah, but will they give him any partners?
It's not that's something that like that's something that like a few more summation, right? Yeah.